Hello and welcome. My name is Keith Barker. It's so good to have you here. I was chatting with a couple of people after the live stream. Not just a couple of people. I was chatting with Dave and Brendan, and I think Packet Thrower was there in the mix as well. And one of the questions that came up was, I'm trying to connect my home network. They bought some Cisco gear. I'm trying to connect I think it was Brendan, trying to connect my home network, my Cisco gear, up to the live internet. And so I said, let me help you out. I'd love to jump in there and play and tinker. Well, it occurred to me when I did that there's a lot of stuff that's going on to make that happen. For example, routing, not just on the routers, but also on the local PC on your local network. If you want to make that all manageable by that PC, there's NAT that's going to be required, or its little cousin PAT, and also and routing. I mentioned the routing on the PC or on the router itself that would have to be done. So I thought, you know what? Let me do this. In fact, I asked Brendan in the chat, hey, do you mind if I take this idea and just run with it? So here's what I did. I dusted off a couple of pieces of old gear, an old router and I forget the model, and also like a 3560 multi-layer switch, dusted it off, and I powered them on there, all this noise. So what I did was I connected them with some base IP connectivity to my local network. They're a couple rooms away just for noise purposes. But other than that, they have not been configured. So let me introduce you to the topology. And what I'd like to do, if you're in for it, I'd like to walk you through step by step how to connect a home Cisco lab that you've built to the internet and have it use its own separate subnet and be able to manage its routes and stuff within that space as well. And I think you'll enjoy a lot of the pieces. All right, let's take a look at the topology. So here's the topology. And let me get out my pen here. There it is. All right, so here's the topology we're going to use, and this mirrors my current network here at my house, at my recording studio. And let's take a look at the pieces. So this is the internet. I think we're familiar with that. And then the internet comes into, I have a cable modem, but could be a DSL device. It's the device that terminates to the service provider network. And then it has a connection to my home router. Now, some devices or devices would have the cable modem and DSL built into the router itself, and there's also possibly wireless that's coming off of that as well, which is all great. But I just want to give you the lay of the land as far as my cable modem, DSL, and my home router. And in my case, I'm using Google Wi-Fi here at this location. And so on my internal network at my home office here, I have the 192.168.1 network with the 24-bit mask, and I've got .1 is the IP address of the actual router itself. So that's my default gateway. Now it's running DHCP. But what I chose to do is on my PC here, the one I'm currently sitting at, it has the IP address of .254, and I statically configured that. In fact, let's just pause for a moment and confirm that. So I'll bring up a command prompt, and we'll do an IP config. And just to verify that I've got that IP address that I think I do, sure enough, there's 192.168.1.254. That's the IP address on this PC that I'm sitting at, and the default gateway is 192.168.1.1, which is the IP address of my Google Wi-Fi router system. Okay, want to make sure that was set. It is. All right, moving forward. Okay, so then what I did was I connected router 1 on its FA00 interface. I physically connected that into this network. Now, out in my other room, I've got another Google Wi-Fi node, and it has an Ethernet port. I just plugged it in. So I have this physically plugged in the router into this 192.168.1 network, and I also assigned it hard-coded. I could have done DHCP, but I wanted to know what the address is every time, so I gave it an IP address of .11 that wasn't in use, and that's how it's starting. That's its starting position. So there's this home network. There's the router. What I also did, so I could remotely connect all that other stuff, I also took the switch. Now, the switch is connected to the router. Router's using FA0/1, going to a gigabit 0/1. They'll negotiate that speed and duplex, no problem. But on this 0/1 interface, that's the physical connection. I also configured on switch 1 all the ports are associated with VLAN 1 by default, including this one. And I also carved out interface VLAN 1. And on this network, it's 172.16.1.0 with the 24-bit mask, and I use .200 here. Now. let's back up the truck for a minute. If you're looking at this and you're brand new to Cisco, brand new to networking, and you're thinking, what the heck is all half of that stuff? No worries. I've got a whole master playlist on YouTube. You can go through it. It's the master playlist for CCNA 200-301, and that'll walk you through step by step a lot of these pieces. And the cool thing about a lab like this, if somebody's trying to do it, is it's going to require a lot of different technologies that we've learned in the course of CCNA to put it together. That's why I think it's a great rehearsal for practicing a lot of the technologies. So coming back here, that's the initial position. And let me see, what else do I have here? Oh, and also what Brendelin said is that they want to use like the 172.16.1 network and 2 network and 3 network and so forth. So after we have this initially configured, I'll also share with you how to set up a route on this PC. So this PC knows, oh, if I need to reach 172.16 anything, I need to forward it over to .11. So we'll refer to this diagram as we build the network. And let's start off with R1, which should be at the IP address of 192.168.1.0 or 1.11 on this interface. And here it is. Let me show you. I haven't used this in a while, as I'm picking up papers. I haven't used this cable in a while, but I did today. So this is a USB connection on one side that goes to the console port on a Cisco device. So what I did was I just wiped out the configs on router 1 and switch 1, put on the base IP addresses for the VLAN interface and for FA00 and FA01 so I could remotely connect to them. And then everything else is going to be from the ground up, similar to what you'd experience if you're doing this on your own with having to configure all the NAT and the routing protocols. Okay, so let's hide that pointer and let me bring up a session and let me verify. Wow, I can't. Let me connect to R1. So I installed PuTTY, which is free, and all right, there he is. So I'm connected to right now. I'm connected to the IP address of R1 on its .11 interface. And to verify that, let me just resize this again. Super. Okay, so let's do a show IP interface brief. So there's the FA00 interface that is connecting me or connecting this router to my little home network. And then this is the 172.16.1 interface that is connecting the router to the Cisco lab network. So if we looked at the topology again, let me go ahead and actually click on this. So if we clicked on the topology, what we're looking at is FA00 and FA01. So the first order of business, if we want to have our Cisco lab connect to the internet, R1 is the key pin in making all that happen. And as we take a look at R1, if it doesn't have any routes outside of its locally connected networks, so what we're going to need to do is set a route to 0000. That's a default route. And I've got a question for you. Let me have you go ahead and take a stab at this. If we told R1, hey, dear Minister R1, with a static default route, if you don't know how to forward a packet, where should it go? And what IP address would we use as the next hop if we wanted to set this default route for R1? And again, this is so we can get the home lab to reach the internet. What would be the next hop for the default route? And you're saying, Keith, it looks like it would be .1, because that is the only way out of this local network. You would be absolutely correct. So we're going to create a static route on R1, a default route that says to get to anywhere, meaning you don't have a more specific route in your routing table. You're going to use 192.168.1.1, which is our home router. It's the same default gateway it's the same IP address that we're using on this PC as a default gateway. So let's clean that up. Let's go back to PuTTY and let's do a show IP route to start. So we've got two routes. They're two directly connected networks, the 192.168.1 and the 172.16.1. And to create a static route, we're going to do this configuration mode, IP route, and then we're going to put in the 4 octets of zeros, space 4 octets of zeros, which is the syntax for a default route for IPv4, and then the next hop address of 192.168.1 dot. We're going to point to our home network's IP address of our router, which in my case is .1. So then, now that we've done that, we should be able to ping, and I like to start small, so meaning baby steps. So let's do a ping to the default gateway, 192.168.1.1, the IP address of my router. I say that my home router. And, okay, great. So the first one was consumed by the ARP, and then the rest should work great. And let's also try to ping my PC. Now let's take a look at my PC IP address, which is .254. Again, the secret here is just starting small. Same local network. We're not really worried about routing outside of our network yet. Just to make sure that the basic pieces work, and then you can document that and move forward. Sometimes people throw in configs and they throw in devices, and then things don't work. Like, what's that? So if we start small, verify the infrastructure that it's working. We have reachability to things on the same network. That's a great, great first step. All right, so back to PuTTY. Let's do a ping to 192.168.1.254. And that's not working. No, not working. So why not? Why is that not working? And if you've had some experience with Windows devices, you may know that a Windows computer has many times, in fact, I think almost all the time, by default, a firewall attitude built into it where it's not going to accept ping requests and it's not responding. So this could be a false indicator. And I want to point that out because you're very likely going to run into this if you have a Windows device. So check this out. If we did a show ARP, look at this. See that right there? That means that this router did an ARP request, got the response, and if we look at the MAC address on my Windows computer, it's going to end in C042. And that means that we're on the same network. It's just that my computer chose not to go ahead and respond. So one answer to that is to go to your computer. So I'm going to bring up a command prompt on my local computer. Let's verify the IP address. So I've got a lot of things going on, but this is the primary IP address on that network. And let's do a ping to the router. A ping to, I'm going to call it R1 going forward. That way we'll know it's a Cisco router. So we'll do a ping to R1's address, which is, it's right there. It's 192.168.1.11. 192.168.1.11. And see how that works? That just takes a whole bunch of like frustration and pain out of the scenario, because a lot of times when the PC or when the router can't ping the PC, it's like, oh no, something's broken. And in Windows, it's just likely the personal firewall that's running on that device by default. Okay, so here's what we've done so far. We have verified that R1 can ping the PC, or the PC can ping the router, and the router can ping this IP address of .1, and that local part is good. So let's move along to, let's verify that R1 can get out to the internet. R1 has a default route that says use .1 as the next hop. Let's verify that that works. That'd be a good basic starter as well. So back to the router we go, and show IP route. So here's our default route right here. I'm in kind of a interesting version of iOS. I don't know how old this is, but anyway, literally this switch was sitting in a closet and not being used for a long time. Anyway, this default route is using the next hop of .1. Let's do a ping to 8888. And sometimes I think, you know, is that real? Is that like, did that really happen? And let's do a trace because it was pretty fast. We'll do a trace out to 8888. And sure enough, all right. So there's the default gate. There's the default gateway, the .1 address, or the default route address. There's the next hop, which is from my service provider network. So they're also doing that a couple of times, it looks like, for me. And then I have the next hop and the next hop. Looks like I had a firewall or some of their devices said, I'm not responding to your TTL expired messages, which is often quite normal. And then we have our final destination here, which responded back. So we literally have this router, which is sitting out in my hall, connected through my home network out to the live internet. Okay, so what's next? Next, let's configure, let's take a look at switch 1. And it has an IP address on its switched virtual interface. That's a logical layer 3 interface for VLAN 1 of 172.16.1.200. And let's just verify we have basic connectivity between R1 and that switch. So to do that, I have a telnet. I have a okay. So to do that, because I don't have full connectivity from my home network to that switch on the Cisco Lab network, from R1, we're going to telnet from R1 and hop over to switch 1. So it's going to look something like this. So we're sitting here at R1. I'll use a different color. We're sitting here at R1, and what we're going to do is open a telnet session to go over to that IP address of the switch, which is enabled and accepting telnet sessions. Also, if you've currently set up SSH and that's working, you could use SSH as well. I just did this so I wouldn't have to take my console port, my console cable, and plug into that switch to do the config. I wanted to do it with the noise of those devices in another room. All right, so let's do that. Let's go ahead and on R1, we'll do a telnet to, what was the address again? Let's take a look. The SVI address, the switch virtual interface address for VLAN 1 of the switch is 172.16.1.200. And from a router, we could type in telnet 172.16.1.1.200 is the IP address. We could do that, or if we just typed in the IP address 172.16.2.200, Keith, 1.200, if we did that, it assumes we want to telnet, and it'll launch telnet to that IP address. Okay, I was nervous. But anyway, there we go. We have the connection, and if we do a show users, this says, hey, you are connected to me on line VTY0 at coming in from 172.16.1.11, which is the router's address. So I just want to share with you that that's our current session telnet from the router over to the switch SVI so we can manage it and configure it. If you're doing this in your home lab, just take that console cable, if they're sitting next to you, plug into the console port, do it all from there. I just want to make sure that as I showed you this, I'm sharing with you all the details of what I'm doing to make this all work. So let's do a show IP route. Okay, well, so this switch really is a multi-layer switch, but that show IP route where it says default gateway is not set, that's it. That is implying that IP routing is not enabled. So I'm going to enable IP routing on this multi-layer switch so it can route for other devices. So IP routing, that's it, okay. And then if we do a show IP route, also, oh, I know what it is. You know how I'm not getting any messages, console messages, and that's an important aspect. If you're remotely connected to a device through SSH or through telnet, it's not by default sending the messages to your current session. And I may want those, especially I do want those. I like to see the messages that talk about OSPF neighborships and other things. So to solve that, the command right here from privilege mode, not config, but from privilege mode is terminal space monitor. It basically says, hey, please go ahead and send console messages to this session I'm currently using to connect, which in our case is telnet. And that way we'll get log messages. To confirm that, there we go. So great. I just want to make sure we're getting the log messages. And I'm also going to do that over on R1 in a moment too when we go back there. Okay, so where was I? Okay, so show IP route. Show IP route. I said it but didn't spell it. So now it's enabled for IP routing. It has these routing codes, but it only shows us the one directly connected network, the 172.16.1, which is associated with VLAN 1, the VLAN 1 interface. So let's so a couple options here. Let's talk about a plan and then we'll do it. And any way you want to do this is great. I want to share with you some of the options that I think are worth considering, and they would include this. If we're going to build more networks back here, like the 172.16.1 and other routers, maybe we hang a router off here and hang a router off here. If we want those routers to also have reachability and be able to reach the internet, what we're going to want to do is run a dynamic routing protocol. And that way they'll be able to dynamically learn routes. And we'd also want R1 to make sure it injects its default route. So it currently has a default route that says, hey, if I don't have a better route, I know to go to .1. But we also want to advertise that inside of a routing protocol so that this router over here, R2 or R3, or even this guy, the multi-layer switch who's doing routing, so it would also know how to forward a packet if it didn't have a more detailed routes. So the one way of doing that would be to run OSPF. And in the master playlist, we have lots of videos on OSPF. It's open shortest path first. It's a dynamic routing protocol. It happens to be link state. And so what I think we had to do is we had to enable OSPF on these two routers, switch 1 and R1 and future routers as well. And we'll also tell R1 to inject a default route into OSPF so that switch 1 will also receive and learn that dynamic route, that default route dynamically instead of having to configure it manually. So that's a mouthful. This is a good review though of a lot of those technologies. Let's enable OSPF on these devices. So we'll go back to switch 1 and show IP interface brief. So all we have is this one interface right here, VLAN 1 interface. And let's also do a ping of R1 at 172.16.1.11. And because we're actually telnetted from R1 to this switch, that implies connectivity as well. So let's do a config T router OSPF 1 for OSPF routing process number 1. And let's just do a network statement for everything. Network 0000 space and 4 octets of wildcard masks. If you haven't seen the wildcard mask videos yet, check those out. They're all in the master playlist, and we're going to put all those interfaces into area 0. The way a network statement works with OSPF is network statement says which interfaces should I consider to be put into the OSPF routing process. And with this network statement, it says any interface that's running IPv4, put it in the OSPF routing process and associate those networks with area 0. So that is done. Also, right here, because I do have some if you have some gigabit links that you're going to be using in your network, you'd also want to do an auto cost reference bandwidth, and I will save the discussion of that for one of the other OSPF videos in the master playlist. All right, so let's do a show IP OSPF interface brief. Great. So we have one interface, the VLAN 1 interface, that's associated with area 0. Here's that's the IP address / mask associated with that interface, and it's currently in a wait state, and that's because it didn't see any other routers on that network segment, and that's because we haven't enabled router 1 yet. So after a period of time, it'll figure out, hey, there's nobody else here. It'll become a designated router because the network type is broadcast, and it'll start running OSPF. So let's go back to R1. And here on R1, we're going to do a terminal monitor because I want to see the messages as they come up. And let's see here. Okay, router, we want to enable OSPF. So config T, router, OSPF. We want to enable OSPF. So router OSPF process ID 1. And the thing here is that sometimes the mistake is made, and we don't want to make the same mistake. The mistake is made that, oh, all I need to do is enable OSPF for the 172.16 interface here, but that's not the case. That's not the case, because as we build this network, if we want this switch or these other routers to be managed by this PC, these other routers need to route back to the 192.168 network, or they could use the default route advertised by R1. But in any case, to play it as safe as you can, I'm going to include both interfaces inside of OSPF. That way we're advertising this 192.168 network in our Cisco lab network, so they'll have that in their routing tables. So I would recommend doing that as well. Later, if you want to peel that back, you can. But let's get functionality first, and then we'll go ahead and pull that back later. All right, so back at the CLI, we'll do a network statement of everything. Area 0, all that, and then we'll do the auto cost reference bandwidth. Set that to 1,000. All that says is that a gigabit interface will have a cost of 1, fast Ethernet will have a cost of 10, instead of everything of fast Ethernet and faster all having a cost of 1, which is not correct. All right, so I don't see a neighborship. So let's do a show IP OSPF interface brief. Oh, it's okay. Oh, so FA00. Huh. Oh, it says BDR. That looks good. Do I have terminal monitor on? I didn't get a neighborship statement. Usually you get a OSPF neighbor adjacency, but I didn't see that at all. Let's. I did terminal monitor though, right? Yeah. So. Oh. Okay. All right. And the problems start. Okay. This was not intended to be a troubleshooting lab, but let's take a look at this output. This is router 1 on its FA0/1 interface. That goes over to switch 1. This right here says that the first number is for F for full adjacency, which it says 0, and then C is for count. That's other OSPF speakers. So R1 is saying that he is a BDR on this network, on that interface, but we don't have a full adjacency. that is a problem. So let's do a show IP OSPF neighbor. Yeah. So maybe if we get out of this stuck state. So right now, what this is saying is we had a video on neighbor states for OSPF, and it goes something like this: IT elf. Like, and I use the little image of an IT elf at Christmas time or a holiday time handing out gifts. So the states that neighbors go through on their way to becoming fully adjacent and sharing their entire release. Oh, there we go. Okay, yeah, they never got past Xstart, and I lost connectivity. Well, let me keep writing out here. So the process is they go through init, then the two-way, then the xstart and exchange. We got stopped at xstart, and then they go to loading, assuming it's working, and then they go to full. But I've got bigger problems. So let's go ahead and sort that out. We lost our connectivity. Yeah, I'm toast. I wonder why that happened. Let's, I'm going to close that. I'm going to reopen. Now, if you're on the console port, you're set. You don't have to worry about reachability to get there. Let's go back to R1. And, show IP OSPF. Here's a couple commands for OSPF, some of my favorites. We'll go back to the show IP protocols. That shows you what routing protocols you're running. So this shows our network statement. And we'll do a show IP OSPF interface brief, one of my favorites. This shows us that we are the designated router on both of these interfaces, but check this out. We do not have a full adjacency over with the switch. So I'm going to do terminal monitor again. And let's do, I'm just bringing this up. I don't know why it's not seeing a full adjacency. All right, this is not something you should have to do, but it's my home lab here, so I'm going to do a debug of IP OSPF. So I'm going to do packets. I can do packets. It's the adjacency that we're trying to troubleshoot. So let's do a debug IP OSPF adjacency and see if that tells. Let's do a, Okay, I'm going to turn that off because that's all I need to know. Undebug all is a fast way to turn that feature off, debugging off. And this says state xstart. We saw that, and they didn't get further than that. Oh, it says right here. Look at that. Neighbor 172.16.1.200 has a larger interface MTU, and that's why it's failing. Wow. Okay. If you're in a CCA lab or a CCNP lab, perhaps this would be appropriate. For CCNA, this is, oh my gosh, I just lost connectivity again. Okay, so what we need to do is, I'll reconnect in a moment. What we need to do is I need to go and tell this interface right here to ignore the fact, for OSPF, ignore the fact that the MTU, the maximum transmission unit, is larger. And I think it said 1504. I'm just going to go ahead and tell it to, we could either go to switch and set it down smaller, or we could just tell 0/1 to forget it. Don't worry about it. Let it go. And I think he will. At least that's the way it used to work. Let's go ahead and verify that. Okay. All right. On the road. Yeah, that session is dead. We'll right click here. And let me see if I can do a reset terminal. No, it's gone. All right. I don't know why that's happening, but it seemed to happen when the errors came up. So we'll go back to PuTTY, go back to R1. All right, let's work quick here. We want to go to interface. Let's leave this right here while we do it. We want to go to interface FA 0/1, and I'm going to do terminal monitor. That's just so I can see the messages. And let's do a IP OSPF. Oh, there it is. MTU ignore, just like that. So if that was the only problem that was causing us not to neighbor up, oh, there we go. There's our full adjacency right there. Oh no, it's not. From down to down. Okay, there's our full adjacency. Okay, I wasn't expecting that, but there it is. I can live with that. And if stuff comes up like that, hopefully in your environment, well, if it happened here on this 3560 switch, because the MTU is different for the VLAN interface than the router interface, now you know the secret to solving that. On the interface, just go IP OSPF MTU ignore. Okay, now let's next go back to the switch. And the switch is at... All right, now we're in the weeds. We'll go to the switch's virtual interface of 172.16.1.200. Great. And I set up the VTY lines on switch 1 so that no login is required. Puts me in privilege level 15 immediately, so that's what I did there. And let's do a show IP route. look, okay, so we have this route of 192.168.1, which is this network right here, which is great. So now this switch knows how to reach this network, but it doesn't have a default route. And so we want to inject a default route in OSPF as well for everything else, including the internet. So to do that, let's go back to R1, and I'll leave this up here. So I'll type in exit. We'll go back to router 1 and config t router OSPF 1. And one way of doing this, because R1 has a default route, do show IP route static. So there's its default route. And if it has a default route, we can, in the router process, just do default information, originate always. And the always keyword, you don't have to tack that on, but what that says is, hey, Mr. R1, advertise the default route if you got one. That's the first part. And then the always keyword says just, even if you don't have one, just advertise the default route so that everybody thinks you know where to go for anything that's not more explicit in the routing tables. So I'm going to throw on the always in case for some reason we're playing with static routes and we remove it off of R1. And now that we've done that, I'm going to do a WR. Let's copy run start, the old write memory command. And let's also go to a switch 1, 172.16.1.200. And we'll do a write mem. And let's do a show IP route. Okay, and there is our OSPF route right there. The default route for everything. So that means that this... okay, so now let's take a big picture look at this because we're not done yet. And this is why it's important to go through all these details. Let me bring up my pen. All right, having fun, getting serious. So switch 1, if we tried to ping 8888 or did a trace to 8888 out on the internet, it's going to look at its routing table. It's going to look for a detailed route, a specific route for 88 something. It's not there. It would default to the default route, and it would forward it to .11. So switch 1 would make a routing decision using R1 as the next hop. Then R1, it would say, and we can go take a look. I'm going to take off my pen there. So R1 would say, I was expecting more routes, but we haven't got a lot more routes yet. So R1, if it got that packet, it would look for a specific route for 8888 or any kind of a route that matches anything. It's not there. It would use its default route. It would send it to 192.168.1.1, which is my little home router. And then my little home router would say, oh, you're trying to go to 8888. It would forward through the ISP. Let me clear this up and show you. It would go ahead, my home router, and forward up to the ISP, up to 8, and then the internet and all of its devices and all the routers and service providers would forward it and do other things along the way. Now, the question is that going to work? Can switch 1 ping 8888 and successfully get a response? And the answer is, let's look at the return path, and I'll let you tell me what the answer is. So if we did a ping to 8888, at this DSL box, our home router is probably doing NAT or PAT. So it's going to swap out these private IP addresses either here or somewhere along the way on the internet before it gets out. So if the packet makes it out and the reply comes back here to the home router, and check out what the reply address is. It's this guy, 172.16.1.200. And you know what your little home router says to that? I don't know where that is. It doesn't. It has no clue how to reach 172.16. There's no, at least going this direction. It might think it's going to use like out to the internet, but it doesn't know it's over here. And so at that point, the reply won't get back, and switch 1 and your whole Cisco network no longer is not going to have access to the internet. R1 will, because it's on this local network that the home router knows how to reach, but all these guys don't. So to solve that, and this is what we're going to do next, is let's test it. Let's test the ping and verify it fails. So we'll go back to switch 1, IP host. Is it IP host? Is that not allowed? Oh yeah, IP host SW1 172.16. Oh come on, Keith. 1.200. Awesome. Save that. The reason I'm going to do that, I'm tired of typing in switch 1's IP address. So now what we can do is just type in telnet to SW1, or we can just type in SW1. It would telnet there. And now we're there at switch 1. Okay, so if we did a show, we already did the route. So ping 8888. Yeah. So that packet's actually going out to the internet. and it's being netted along the way by either my home router or the ISP going out. But the reply traffic coming back when our router sees it, our little home router, it has no idea where the source address of 172.16.1 is. So to solve that, we're going to have to implement NAT. And here's what we're going to do for our NAT plan. And I will add this. I will add this permanently on this. Actually, let me make one more layer. And I'll add this in because we're going to need to keep this if we want it to work. So let me bring out some colors. And let's use light blue. That'll work. So from a NAT perspective, what we're going to do is we're going to have this part of the network. I'm not happy. I'm not happy with that color. I'm not happy. Let me change the color. All right, here we go. So from this perspective, it's going to be, for NAT, this is going to represent the inside. And over here is going to represent the outside from this router's perspective. So we can set up a NAT rule that says, hey, anything that is 172.16 anything qualifies for NAT. This will be the inside interface. This will be the outside interface. And if we see traffic like that, we'll just translate it, and we'll just translate it to our IP address that's on this interface of .11. And then when that packet goes out the home router with the next top of .1 and goes out to the internet after a couple layers of NAT that the service provider is going to do, when the reply traffic comes back to 192.168.1.11, which is the NATed address for switch 1 and for anybody else, because we're going to be using PAT, it would say, oh, I know where that is. It would forward the packet back to R1, who would then untranslate it and forward it to our home network, or to this Cisco network. So we're actually going to use PAT, port address translation. This is a great exercise too, if we want it to work. If you don't want it to work, don't do it. But this is all these pieces are good practice in implementing the technologies in CCNA 200-301. So if you haven't joined our if you haven't yet, please click on subscribe. Hit the alert bell. I drop videos 2 to 3 times a week. I add them to the master playlist. They're lots of fun, so I want you to enjoy them as well. All right, so let's invoke NAT here on R1. Now I have a separate video in the playlist that goes step by step implementing inside source NAT, which is what we're going to do right here. So I'm just going to implement it to verify that that's what's required, get it working, and then you can either go back and review the steps slowly or go back to the video in the master playlist on NAT and enjoy it more. I'll also probably make a packet tracer and a Viral 2 lab that walks through some of the details for NAT as well. Viral 2 drops in April of this year, this month, and I've never been so excited for a Cisco product in my life. It's going to be great. Okay, let's implement NAT. The plan is we're allowing everything on the 172.16.1 network to be actually, oh, you know what? Let me tweak this while we're here. This is the 172.16.1 network. So maybe out here, this is also VLAN 1. That would work. And then this could be VLAN 2, and this could be VLAN 3. I thought, oh no, I've got these networked in the same place, but they could be part of the same VLAN. So this could be VLAN 1, and this could be VLAN 1. I'll leave it. Let's implement NAT. And to do that, we'll bring up the CLI. And I will let us see the picture here. That way we can see the graphic as we configure it. And let's create an access control list that identifies who can be translated. So access list 1, permit. And we're going to say 172.16 anything. So our wildcard mask will be, actually it's a wildcard bit at this point, wildcard bits will be 00.255.255, which means anything that starts with 172.16 qualifies for NAT. And we'll press enter. Boom, done. We'll tell R1 that FA00 is the outside interface for NAT. IP NAT outside. We'll tell this router that the inside interface is FA0/1. IP NAT inside, like that. And then we'll set up a rule that says this, IP NAT inside source list. If any traffic coming in on an inside interface matches access list 1, which is looking for 172.16 anything, go ahead and translate them to, I don't have a pool of addresses, we're going to use the one IP address on the interface of R1, which is this interface right here. This interface right here. So IPNet inside source list 1, interface, and I'm going to say FA0/0, and I'm going to scooch this over so you can see this as well, because the next part we're going to put in is overload, which means do it again and again. You can put hundreds, thousands even, of IP addresses to that one IP address, and port address translation will come to the rescue to keep all those sessions unique. So there's that. Again, check out the master playlist for more details on NAT, as well as OSPF, as well as VLANs, and SVIs, switch virtual interfaces as well. Okay, so now that's done, let's do a show NAT statistics. This is a great way to see the kind of the details. So the outside interface is FA00, inside interface is FA0/1. There's the access control list, great. And let's go back to switch 1, and let's try going to the internet. Yeah. Okay, so let's do a trace out to 8.8.8.8. You know, it's freaking amazing how fast things work. I mean, this is a router. This switch is going through a router that's then going through my home network, which is then going to the service provider, going through a couple levels of NAT there, or PAT, whatever they're doing, and then sending it out to the internet. And if we do that again, a Cisco router uses UDP at layer 4 when it does a trace command. And so if we went back to R1, and I'll just type in exit to get there. We could also swap between sessions, but let's do a show IP NAT translations. And yeah, that's a lot because we had 3. You have 3 for each hop in the path. So there's our translated. So we also have another video, which is, I thought, a lot of fun, about inside local and outside global and inside global. What do they mean? When I think it'd be good for a review real quick right here, because it'll only take a moment. We got it right here in front of us. Anywhere it says local, I want you to think of a user on the inside, somewhere over here, that is looking at the IP addresses. So from the inside user, the local user, thinks that the inside address is 172.16.1.200, which is the IP address on SVI1. It really is. And it thinks we're going to the outside address of 8888, which is literally true. But that's the perspective from the inside, looking at those addresses. If we used a different color to help visually separate these, and I will go for, let's go for green. If we're looking at this from the outside, the word global is from the perspective of the outside, somebody out here looking at the addresses involved. So from the outside, they think, oh, this packet is destined to 8888, which it was. That's because we were not doing destination NAT. We didn't translate the outside address, so it's going to be the same from the perspective of the inside or the outside. But from the outside's perspective, if we went right now and said, hey, Google, who do you think the IP address was that was making that request? It's right here. From the outside position, it would think, oh, that inside address looks like it came from 192.168.1.11. Now, that address, it went through several layers of NAT as it proceeded through my cable modem and the internet service provider. But that's a quick review or discussion about Larry's local. What does it look like from the inside? G is for Google or some global company, saying what is its IP address, what do the addresses appear as from its outside perspective. And from this router, that's the dividing line. From the inside perspective, what do things look like as far as the IP addresses? And here from the global perspective, what do the IP addresses look like? Local is the appearance from the left. Global is the appearance from the right, the outside. And I think that worked. Actually, I'm sure it worked. We just did it. So in this video, I wanted to share with you, wow, we got everything. Let me just make sure I got my notes. Routing. Oh, no. Stop the truck, Keith. There's one other important aspect I want to share with you. Let's do it right now. And that is this. If we want this PC, so at the moment, let me undo that. Let me get out my other pen. There we go. So if we want this PC right here to be able to reach switch 1 directly at 172.16.1, this switch 1 knows how to get to this network where the PC is, but the PC does not know how to get to 172.16 at all. And we might have 172.16, the 1 subnet for VLAN 1 and 2 for VLAN 2 and 3 for VLAN 3 and so forth. So what we could do is create a static route on this PC that expresses or says how to get to those additional VLANs. And sorry, I think so. If we could create my brain was like going 3 levels deep. This PC, we need to set up a static route that says, hey, dear Mr. PC, to get to 172.16 anything, go ahead and use .11 as your next hop so it can make correct routing decisions. Otherwise, it'll be trying to send routes out to the .1 address, its default gateway, which will then never reach over here. So that one last step is important if you want this PC to be able to directly manage your other devices in this network. So let's do that. So I'm going to bring up a command prompt. And here's a command prompt. And this is on my local PC here at .254. And let's do a show. Well, I'm just going to do a route print. So route print is a command you can do on a Windows computer to verify and see the entire routing table. So there's lots of information going on. Here's my default route that says the default next hop, the default gateway is 192.168.1.1. Here's how we can add another static route that says use .11. I'll scooch this over to the right a little bit, and I'll speak this as we do it. So it's route, add, I think. Oh yeah, I need to do it from a privileged prompt that has admin rights. So I'm going to go to. So I'm just going to grab my command prompt, right click and say run as administrator, because I'm going to need this so I can actually add a static route on my local PC. So here is the syntax. Route. Okay. route enter. I just want to see the syntax. So we're going to do a route. Where's add? Oh, right there. Okay. So here's the syntax. Route, add. We want to go to 172.16 anything. So we'll use a mask of 16 bits. So that route will cover 172.16, 1, 2, 5, anything that begins with 172.16. And then the next hop address is going to be the router here at 192.168.1.111. Excuse me, 111. Let me scooch this over a little more so we can see it. Then the problem is, and it's a good one. The problem now is that if we add this route and then we reboot our Windows machine, it loses the route. So we're going to add the -P option at the very end. And the -P says, hey, please keep this as a persistent route. So next time I reboot, I will remember it. Not a bad idea. Let's do it. So we'll just add the -P. Oh, bad argument. Route, add. Oh, I forgot the keyword mask. Okay, mask. All right. So then after I've added that route, we'll do a show. Too many Cisco commands. Route print again. And take a look at this. In the persistent route section, it now has a route for 172.16 anything with the next hop of 192.168.1.11, which is our router. So the last step is to verify this. Let me go ahead and close PuTTY. Bye-bye, PuTTY. We'll open up a new PuTTY session. And I guess we could also just ping. I'm going for the home run here, though. Let's do I don't have SSH enabled on switch 1, but we can telnet over there. And it is 172.16.1.200. I'm going to call that switch 1. I'm going to save it. And then I'm going to go ahead and load it and open it. (172.1.200). Okay, maybe I did something wrong. All right, we're going to troubleshoot this live. I'm going to close that session. At my command prompt, let's see if I can ping 172.16.1.200. I can't ping it. I wonder. I don't know why not. I don't know. I thought, okay, we'll do all this lab, we'll connect it all, but I really would like this piece to work. So let's find out what's going on. Let's bring back PuTTY. I'm going to go directly to switch 1. Actually, I'm going to go to R1, then hop over to switch 1. Show IP route. It has a route to 192.168.1, which is where my PC is. Let's see if it can ping. Oh, it shouldn't. Let's see if I can ping my default. Oh, we know that this switch is good to go as far as connectivity. We already did a trace out to the internet. Yep. And let me bring that up a little bit so you can read it. Hey Keith, how did that 20-minute video turn into a 40-minute video? Story of my life, computer networks. All right, let's do this. let's just do a ping to 192.168.1. This is a good trick. 11, which is the router, and which is R1, and we'll go to .1, which is my Google Wi-Fi home router. So why isn't my PC? Maybe my sessions is messed up. Let's go back to. So it's not a routing issue. Switch 1 knows how to route to the 192.168.1 network. This is my PC having grief. So let me exit out of here. Exit out of here. I'll bring up, and let me start up a new session. Maybe I just rushed it. So this is PuTTY. And I'm going to use telnet to 172.16.1. In the replay, I'll have to go back like, what? Did I go to the wrong address? .200 telnet. I'm not going to change any other settings. Open. Oh, I'm connected. Why is it not? Holy spamoli. So I'm actually connected. It's just my terminal isn't working. All right, I'm going to do one more Hail Mary here. I'm going to go back here, take my R1, load it. I'm going to say instead of connecting to 192.168.1.11, I'm going to take those settings, everything else in this terminal session with PuTTY, and I'm going to go to, and it has a route. Okay, so 172.16.1.200, open. Holy spamoli. I am connected. Yeah, it's okay. Well, I say we troubleshoot this. It's going to be a little longer. If you want to cut off now and work on your lab, that's great. I am very curious as to why I can't get there from my PC IP config. Unless I put the wrong route in or something. No, I'm connected. So I am on the 192.168.1 network. I'm at .254. I've got firewall services enabled, so it shouldn't be able to ping me. I'm going to turn off my firewall services for a moment. Just going to go firewall. I'll turn it back on after. Check firewall status, and I'm going to go ahead and say turn it off. Turn Windows, not Defender, firewall back. Okay. All right. Off, off. Okay. And I just want to see if I can ping from switch 1 to this computer. I'm on the same network. That shouldn't be a problem. All right, let's go ahead and let's bring up PuTTY. I'm going to go to R1. That's R1. From there, I'm going to go to switch 1. Let's do a show run real quick here. I'm going to look at these VTY lines. But I'm connected from R1 on the VTY lines. That is so weird. I have got no login on those. I wonder if it's something coming from a non-local network. Okay. Let's do a ping to 192.168.1.254. Yeah, okay. So I've got connectivity. I turned off the firewall so that it would respond to the pings. Why is it that I cannot? See, right now I'm connected from the router. I've got connectivity back to my PC. Why is it that my PC can't telnet directly over to the switch? I don't know. Okay, I'm going to try one more time here. I want to go to 172.16.1.200. I want to use telnet on default port TCP23. I'll take 2. Save. Open. Let's it couldn't be my settings. got it? Hold on a second. Reset terminal. All right. Wow. Why can I not connect there? I wonder if it's something local. So here's what I'm going to do. It is so weird that I have connectivity, but I can't log in from this PC. I really want to. I really do, by the way. I really want to. So, a couple things I'm thinking of, because I have like no login on the switch. I'm thinking, are there any kind of weird parameters for telnet that only allows from local networks? Because it works from R1. It just doesn't work from switch 1, but it's not refusing the connection. Let's do this. Let's do this. Let me, I did this to myself. This is fantastic. Here's what I think's happening. Here's what I think. All right, here's what I think is happening. I think that this PC is initiating a connection to that switch at 172.16.1.200. That's true. And when the reply is coming back, R1 is doing network address translation on that to its own IP address. So this PC is expecting an IP address from switch 1 coming back. And what it's getting is it's getting a reply from this IP address on this interface as it's going through NAT 1 direction. And that's what's happening. Oh my gosh. I was not expecting that. So, how do we fix that? We could do conditional NAT, I suppose. Okay, here's how I'm going to fix it in the short term. There are some options to do conditional NAT based on policy, like where is the traffic going, to NAT or not NAT. But here's what I'm going to do. I'm going to remove the dynamic NAT. I'm going to put a static network address translation for switch 1 right here on R1, and then we'll do a telnet to that IP address. That'll work. Yep, let's do that. Wow, dang. And also the way we could have verified that is if we do that again, that connection, like a bulldog. Don't let go. Don't let go. So if we go to router 1 for a moment, and we go to go to router 1. Let me open up a session again, or try to open a session. Let me move that out of the way. All right, another troubleshooting lab, courtesy of how the network works. And let's so I'm going to put up a new session that's going to try to go out to the switch. And so it's failing. And on R1, if we do a show IP NAT translations, yeah, see that? It's translating 23, that's telnet, TCP port 23. It's translating that back to its own interface address, and that's why I'm getting this response from a device I wasn't asking for. All right, now we know what the problem is. Let's go ahead and solve it right here on R1. Config T, no, IP NAT. Let's do this. Do show run, not snow. Do show run include source. I just want to get the source access list and remove it. We'll do a no, and boom. Do you want to delete all entries? Yes, I do. And then let's just do a static translation. I totally caused this. I was like, yeah. So this will solve it, I believe. So IP NAT inside source. Yeah, we could use a route map to get very specific on when we want the translation to happen, but I'm just going to go ahead and use IP NAT inside source static. And we'll map the address of 172.16.1.200, and we'll map that to the global from the outside perspective. We'll map that to 192.168.1. Let's use 200 again. I say the last octet of 200. So we're going to map switch 1, its VLAN 1 interface of 192.168.1.200 to the outside, or to my local home network address of 192.168.1.200, and it's done. Show IPNAT translations. Okay, so there's our hard-coded translations. It's not in use yet. It's sitting there ready, but we don't have any traffic. And now, if we go back to another session of PuTTY, and we go to switch, actually, I need to change this. I'm going to load it. So we no longer want to connect to 172.168.1.200. We now want to connect to 192.168.1.200 because that's the statically mapped address from our perspective on the outside, and open. And there's our prompt right there. Switch 1 up about time. All right, that's a lot of fun. The last piece with NAT, I wasn't expecting that. I thought, oh, we'll just NAT it and it'll be great. But the reality is that we were connecting from PC over to that IP address, and the response, because it was being NATed for the reply of that traffic, was coming to the other address. And so now we're connecting to it at its mapped address, and we are good to go. All right, whoa, looking at the clock, that was a lot longer than I thought it would be. Hey, I'm glad you joined me. If you enjoy networking, which I do, and you want to join me at Keith Barker up on YouTube for our focus on the technologies. All of these, by the way, are except for the conditional natting. All these are representative of the technologies associated in Cisco CCNA 200-301. Also, if you're looking for a formal course that covers every bell and whistle from soup to dessert, of course, we have CBT Nuggets with 52 hours of training there. It's done by Chuck, Network Chuck, Anthony, Network Chuck, Jeremy Chara, and myself. It also includes labs and everything else. Also, stay tuned on this channel if you liked it or learned something, or you want to follow me more. Click on subscribe, hit the alert bell so you know when new alerts come in or new videos are dropped. I also add new videos and labs probably 2 to 3 times a week fairly consistently, and I'm going to continue doing so. Also, after the premieres happen, I record them like this one, and I'll premiere it at a certain time so I can sit there and watch it with you and chat. I also often, if I'm available, will often have a voice call afterwards so we can chat about it, ask questions, and discuss it in Discord, on the Discord server. So I'll put links for the Discord at the bottom as well, so you can join that if you like. All right, I have taken longer than I intended to for this, but I wanted to thank Brendan and the other individuals involved on Discord when they were asking me about this question and getting it up and running. And I thought that everybody, a lot of people could see value in implementing all these pieces to get it working, including the NAT. All right. Hey, thanks everybody, and I'll see you in the next video. Bye for now.